Hello everyone. In the last lecture we have discussed about the plastic waves of uniaxial stress. We discussed about the simplest experiment to generate plastic waves developed by von Karman and Dewey. So this lecture we will discuss plastic waves of combined stress, that means both shear and longitudinal plastic waves, and also we will discuss about Taylor's experiment, that is impact of finite length bars, and another part of the plastic wave, that is the plastic wave of uniaxial strain, we will discuss later. So what we discussed earlier is plastic waves of uniaxial stress. So we have already discussed, and so the plastic waves of uniaxial strain, which is like shock waves, so we will discuss later. And today we will discuss about the plastic wave of combined stress, that is both shear and longitudinal plastic waves. So plastic shear wave, like the elastic shear wave, that involves the particle displacement in a perpendicular direction to the direction of propagation of wave. So as we know, shear waves, the particle movement is perpendicular to the direction of propagation of wave. So this is true for both elastic and plastic. But in the case of plastic, as we know, the particle displacement are permanent. That is permanent displacements. So the researchers have developed different experiments to generate plastic shear wave. So experiments to generate plastic shear wave, only plastic shear wave, is not very convenient, and generally the experiments have both plastic shear wave and plastic longitudinal wave combined. So that's what we have this title, the plastic waves of combined stress. So we will have both plastic shear and plastic longitudinal wave. So we will first talk about Lipkin and Clifton experiment. Lipkin and Clifton experiment. This experiment can generate both plastic shear plus plastic longitudinal wave. So this is Clifton is from the Brown University. So the experiment, the setup looks like this. So we have a striker bar. So this is the base of this experiment. So this is the striker bar. I'll write just striker, and which will strikes a transmitter bar, which is connected to the base like this, and this is a transmitter bar, and there will be one specimen which is the specimen which is tubular, and then there will be the mounting assembly to produce torque. So the specimen is also fixed with the this is the fixtures that that holds the transmitter bar and specimen bar with the base, and this striker bar will be inside a case, that is the barrel. So that is probably the gas gun barrel or compress with the help of compressed gas. So this striker bar will strike the transmitter bar. So this is we call a rear mount assembly. So first torsion is exerted exerted by rear mounting assembly. I will write rear RMA by RMA. So that torque is beyond the yield strength, because we want to produce some plastic shear wave. So this torque beyond its yield strength. So then after the torsion is exerted, so will hit the transmitter bar with the help of the striker. So this is, we have compressed gas. There is actually a gas gun. Compressed gas gun will move the striker, and that will hit the transmitter bar. This is the specimen is already torsioned. Torque was applied here. So, and after this impact, second phase is the impact. So striker hits the transmitter bar, and transmitter bar hits the tubular specimen. So also this the wave will reflect from this interface, transmitter specimen interface, and both longitudinal and shear wave will elastic wave will reflect from this interface, but it will also transmit to the specimen and producing the longitudinal wave, both elastic and plastic, because it is hit at a very, the impact is at a very high velocity. So and then this rear mount assembly will will produce the torsion. So that means both plastic shear and plastic longitudinal wave will be generated in this experiment. So now we will talk about one more experiment and developed by the same group, that is Clifton's group in Brown University. Clifton's group from Brown University, Rhode Island, USA. So here in this case, this is a barrel. So this one is a barrel. It's a gun barrel, and the projectile from the gun barrel is called a sabot. The entire this portion is called a sabot. You can see the mechanism here to move the sabot inside the barrel at very high speed. So this is moving in this direction, and this is the target. This is the target. So this is also an experiment to generate plastic wave, and this is called oblique plate impact experiment, or it is also known as pressure shear experiment or pressure shear plate impact. So the part of the sabot, this part, this is called flyer plate. So that is a part of the sabot. The flyer plate will actually hit the target, and the flyer plate orientation is flyer plate orientation is not normal to the sabot direction, the direction of movement of the sabot. Movement of the sabot. However, fire plate is parallel to the target. So this fire plate is, the orientation is not normal to the movement of the sabot, but parallel to target. So this is parallel, flyer plate is parallel to target, and that's why it is called oblique and parallel impact. So that is why it's called oblique and parallel impact. So in a way it is oblique because the flyer plate orientation is not normal or perpendicular to the sabot movement direction, and another way is it is parallel. It is called parallel because this sabot, actually the flyer plate which is on front side of the support is parallel to the target. So this is called oblique and parallel impact. So upon impact, stress waves generated from that interface. So we will see how these are generated. So this is, let's say, the target, which is the target is nothing but the actually specimen. Target is the specimen, and this one is the flyer plate. Fire plate. So that is, as you can see, this is a part of the sabot. Fire plate is a part of the sabot. So now this is the impact plane. As you know, upon impact, impact plane, or you can call the interface between the target and the flyer plate. So here the wave in both the direction, both in the target and in the flyer plane, will move in that direction, that is perpendicular to the interface. But if we see different waves, the fastest wave which will be ahead is the elastic longitudinal wave, and the second wave will be plastic longitudinal wave, and third wave is the shear wave. So similarly in other side, in the flyer plate as well, sorry, this is sabot. So in the other side as well, the longitudinal elastic wave will be ahead of longitudinal plastic wave and the shear wave. So shear wave can be both elastic and plastic. So here I will write LE is elastic longitudinal wave, and then LP is plastic longitudinal wave, and then S is shear wave. So if the impact velocity is very high, if impact velocity is high, then the shear wave can be decomposed to elastic and plastic. So basically the impact velocity is high means if the stress amplitude exceeds the shear strength of the material, then the plastic shear wave can also be generated. Many researchers reported, and I think by some researchers it is mentioned that Mashimo and Nagayama reported that this impact velocity is up to 2 km per second, which is very high, can produce plastic shear wave. So to generate plastic shear wave, we need to have very high impact velocity. And as we know here, this wave propagates in perpendicular direction to the impact plane or interface for both target and flyer plate. And also we know that the direction of particle velocity. So particle velocity direction for longitudinal wave, it is perpendicular. For longitudinal wave, it is perpendicular, is particle velocity, and for shear wave it is parallel to the interface, shear wave is parallel to the interface. So, similarly in this case also these are like that. So, basically the particle velocity, as we already discussed this, the particle velocity is perpendicular to wave direction, wave propagation direction for shear, and parallel to wave direction in longitudinal. That is already discussed. So, we have talked about this plastic wave of combined stress, that means both shear plastic wave and longitudinal plastic wave. Now, we will discuss about the split Hopkinson pressure bar, which is actually not known for plastic wave, but still we will discuss that. So, this is the most commonly used experiment to test the constitutive relations or material behavior at high strain rate. So, the split Hopkinson pressure bar, as you can see in the heading, is commonly written, and we will also refer here as SHPB, split Hopkinson pressure bar. So, but one should not consider SHPB not a plastic wave propagation experiment. Plastic wave experiment. So, basically the experimental setup is like this, whatever we earlier have drawn for another experiment, that is to generate plastic shear wave and longitudinal wave. So, it is similar to that. So, here we have first the striker bar, inside a barrel, so this is called striker bar or projectile bar, and this is incident bar, and then we have a small specimen. It is small, means both the diameter are even smaller and the length is very small. So, this is the specimen. So, this is incident bar, this is striker bar. So, and we have another bar which is called transmitter bar, and there will be a something we call as a momentum trap to restrict the movement of the transmitter bar out of the assembly. So, now the specimen is very short. If you see the length of the specimen, very less. So, specimen is short, and if you you can understand from the figure, the striker will be accelerated by a compressed gas, and then this will hit that incident bar. The stress wave will travel, and the stress wave will travel through the incident bar, and then it will hit the specimen, and some part of the wave will reflect back, and some part will go through the specimen, and it will enter the transmitter bar. Now this, due to this stress wave, the specimen will be plastically deformed, and then this wave will continue to go transmit towards the transmitter bar. But although the specimen is plastically deformed, this is not considered as a plastic wave experiment, because the specimen length is very short. So the pulse length is longer than the specimen length. So we do not see any plastic wave actually traveling in this experiment, because the plastic wave propagation configuration is in the specimen is not available. It's a very short specimen. So the split Hopkinson pressure bar is not a plastic wave experiment. It is it handles only the elastic waves, although the specimen is plastically deformed, but this specimen length is very short, and the incident bar and transmitter bar undergoes only elastic deformation. The elastic wave propagates from the incident bar to the transmitter bar through the specimen. So with the help of the strain gauges, what we can get, that we can have a strain gauge here and the strain gauge here, where we can get the transmitted wave, and here we have both incident and the reflected wave. So incident and reflected wave, that is back from the specimen incident specimen and incident bar interface. So we will discuss the split Hopkinson pressure bar in details later. Now we will talk about the Taylor's experiment. So that is Taylor's experiment involves the impact of bars of finite length.